Okay, I want to go over the laws of thermodynamics and kind of give you I think, a clearer description of what entropy is. All right, so the first law of thermodynamics, it's on page 431. And the first law tells us, and it's something that it's kind of universal with every one of our laws, right? Energy cannot be created nor destroyed. Same thing with matter, matter, right? It can only change forms. So when we have a system, and we talked about that with the calorimeter, where that's the point of a calorimeter, is there is energy that can be lost, and so you have it in the insulated cups or in the calorimeter because energy can't be created or destroyed. So when you have the calorimeter, then that way you can assume that all the energy was converted from one thing to the other. So that's all the first law of thermodynamics tells us. Now the second law is a little bit more abstract, and the way that they define entropy, I think, doesn't really help a whole lot with that. And so in the book on page 431, it tells us that entropy, which is S, is a measure of the amount of energy in a system that is not available to do work. All right. That's really kind of hard to understand how we look at that, what do we do with that? All right. So really what entropy is it is the organization of the system. All right. So in other words, if you turn the page and you look at the second law, so we're on page 432, the second law of thermodynamics says the entropy of the universe can never decrease. It must always stay the same or increase. So what that's saying is the order of the universe can never decrease. Okay, the entropy, the amount of disorder can never decrease. Okay, it is always either going to stay the same or increase. So our Earth, our universe, is continuously getting more disorganized. Okay, so entropy it's the amount of work that can't be used or converted into another form, or it's just the level of disorganization. So to make it a little bit more clear, if you look at page 433, we think about our different phases. We think about solid, okay, solid, liquid, and gas. Okay, if we're looking at entropy, which is S, and we're looking at a solid where everything is tightly packed, together, they can't move very much, they're all staying really close together. We look at a liquid, which they're still pretty tightly packed, but they can move around more than in a solid. And then we look at a gas, and we have things all over the place. Okay, in terms of organization, all right, you look at the molecules here, they're nice and organized. They're all in a row, they're all stuck together, they don't move around very much, there's not much chaos. That's another way of saying entropy, is the amount of chaos in it. All right, liquid, they can move around a little bit more. There's a little bit more entropy, meaning more disorganization, more chaos in a liquid with the molecules than in a solid. And then in a gas, it's all chaos. The molecules can move anywhere they want. All right, so when you're looking at entropy, the way to understand entropy is the more chaos there is, the higher the entropy. All right, so what that tells us, and it says in the book too, that, when they came up with this concept, when scientists figured out this concept, they thought that the universe was eternal. Well, we know that it's going to come to an end. It says so in the Bible. And so actually entropy in the second law of thermodynamics tells us that there's going to be an end to the universe. If our order, if chaos is continuously increasing in our universe, then at some point it's going to end. We will not have enough organization for any work to be done. All right. So that gives you a little bit of a hopefully a more understandable definition of what entropy is. So it's more of the chaos. It's work that cannot be used. It's unusable energy. And really it is, the more chaos there is, the less organized there is, the higher the entropy. Okay? So a gas has more entropy than a solid does. A liquid has less entropy than a gas does. All right? And so if you look at the pictures on page 434, okay, if you are trying to figure out which one of those pictures, it looks like either like an hourglass or a barbell or something, and there are molecules in both sides on the bottom one, and there are molecules just in one side on the top one, which one would have more entropy? Well, the one on the bottom would have more entropy because there's more chaos. They are separated by more space. They can be found in either side. In the one on the top, it's more organized because you're only going to find the molecules on one side. So the entropy on and I will hold this, I guess I can put the book up for this, but the entropy on this one would be higher than the entropy on this one because there are more places for the molecules to go, so they spread out more. All right, so there's more room for chaos. Okay, so what we have to take into account with entropy then is we have to look at surroundings and at the system, because what we know from the first law of thermodynamics is energy can't be created or destroyed. So if we have a reaction going on, if our system has an increase in entropy or in chaos, then following our second law of thermodynamics, that the entropy either stays the same or increases, then we know that our surroundings are going to be affected. And here's a better visual for that. So I don't know, maybe some of you still do this, but when you're younger, when you're told to clean your room, all right, you're told to clean your room, you have toys all over the place, so there's a lot of entropy in there, a lot of chaos, all right, and you decide to throw everything in your closet. Okay, so you look at your bedroom and the entropy has decreased in your bedroom. It's organized, it looks great, but the entropy in your closet has now increased by the same amount because now there's disorganization, there's chaos in your closet. So as far as entropy of the universe is concerned, okay, the entropy of the system changed, but the entropy of the surroundings affected it too. And so those have to both be taken into account when you're talking about the overall change in entropy. So we go to page 435 and you look at the pink box, and that's what it tells us. So we have delta S, which is our change in entropy of our system, which our system would be, the chemical equation, the whatever reaction is going on, okay, plus the change in entropy of the surroundings. The surroundings matter. Again, because we're looking at the total universe, okay? And that has to be greater than or equal to 0, all right? So either the entropy is increasing, it's either greater than 0 or it equals 0. Delta S will never be, it's not going to be negative. It's not going to be less than 0, okay? So it's always either